All right, welcome to another deep dive. Today we're taking a look at computational linguistics. I guess you could kind of think of it as like this attempt to really model language, like the structures of language, the meanings, in a way that, machines can work with.
And we have, for this deep dive, a great resource, the Stanford Encyclopedia of Philosophy entry on computational linguistics. And it's a really thorough piece. It gives us a history of the field, talks about the methods, and looks at the different applications of computational linguistics. So, yeah, pretty excited about this one.
Yeah, it seems like it's going to be really interesting, especially for like the philosophical side of things. And our mission here is to kind of like pull out those important insights, like the key moments in how we try to get machines to understand language, which I guess sort of touches on like, big questions about meaning and how we represent knowledge, how language and thought connect, stuff that gets philosophers going. So where do we start with this?
Well, it's really interesting to look back and see how, the early days, like back in the 60s and early 70s, were sort of shaped by this early AI research, right? Systems like SAD SAM, SIR, Student. Maybe they seem basic now, but they were pioneers back then.
Oh, yeah, for sure. And I was reading about those earlier. And they used some pretty interesting techniques, like they'd use pattern matching, breaking down these, little chunks of English and putting info into like relational hierarchies or attribute value lists, and then they'd use that like to answer questions. And they'd use methods like graph search, formal deduction, even, numerical algebra, it might seem simple now, but that was pretty radical back then.
Yeah, absolutely. And one of the conceptually interesting things that emerges is this idea of procedural knowledge. So it's not just that the system has facts, it's about what the system can do with facts, the functions it can perform.
Right, it's not just knowing that a light switch exists, it's knowing how to use it, flip it on and off.
Yeah.
And this procedural knowledge idea really came into its own with systems like Short-Lu and Lunar.
Yeah, Short-Lu. So this is early 70s, and it was operating in this simulated blocks world, which is pretty cool.
Yeah.
And it had this fairly sophisticated procedural grammar, and a set of rules that mapped the structure of sentences to their meaning within this little, contained context. And it could even do some planning using this language called microplanner. And then there was Lunar. Lunar was focused on a database of lunar rock analyses, and it too showed how this procedural approach, had potential, at least within a carefully defined domain.
Yeah, it's almost like they were these really knowledgeable savants, right? They could do amazing things, but only in their very specific little worlds. And that seems to be a big theme in these early systems. As impressive as they were, they kind of hit a wall when it came to expanding beyond their initial little domains, their linguistic abilities, handling more complex real-world language. It just didn't really scale up.
Exactly. And that's the issue of scalability, right? Moving from understanding a few blocks or lunar rocks to the whole of human language was, it was a huge jump.
Yeah, and that kind of leads to this thing that was called the knowledge acquisition bottleneck, right? Which is basically this massive challenge of trying to program in or somehow get a machine to learn all those millions of facts and rules that we humans just seem to know. It's imagine trying to literally teach a computer everything you know about the world. How do you even begin to do that?
It's a massive problem. And, when you consider how much even our everyday common sense is kind of implicit, it's hard to see how you'd even start to formalize all that. And, if you're interested in seeing those foundational efforts, you should check out those classic collections. Minsky's Semantic Information Processing or Schenck and Colby's Computer Models of Thought and Language. They really give you a sense of those early aspirations, the strategies that were tried.
Yeah, it's like a window into those early days. And then, fast forward a couple of decades and things really start to change. In the late 80s, mid 90s, you have this rise of corpus-based statistical methods in natural language processing, right? And this was a total shift in perspective. It was okay, for years we've been trying to teach computers grammar, how we learn it in school, but maybe we should just look at how language is actually used, in real life. Look at those patterns of words and phrases and let the computers learn from that. It was a total change in how they approached the problem.
And it's fascinating to think about what enabled this change. I mean, one thing was just the increasing availability of machine readable text and speech data, right?
Yeah.
So all of a sudden you've got tons of real world language for researchers to analyze, digitized newspapers, transcripts. I mean, it was a huge amount of data.
Right. And there was this like growing realization that like the way language is structured, the way it's actually used, like which words tend to appear together and in what context, those distributional properties, they hold really important clues, to understanding. Plus, you've got all these new statistical learning techniques that were being developed, which like gave researchers the tools they needed to, really analyze these massive amounts of data.
And the big hope was that by like embracing these statistical approaches, they could finally get past those scalability issues that had plagued those earlier rule-based systems, right? So instead of like trying to hard code every little linguistic nuance, the idea was to like let the data speak for itself, let the algorithms find those patterns.
Right. And they actually start to make some really big breakthroughs, like suddenly we have speech recognition systems that were becoming like actually usable, part of speech taggers that could like accurately label words with their grammatical function and even, probabilistic parsers that could analyze sentence structure with a reasonable degree of accuracy. And then you have like machine translation, text-based question answering, summarization systems. They were all becoming like real possibilities.
Though moderate accuracy was often the key phrase in those early days. And while those systems, could process huge amounts of language, their semantic understanding was still pretty limited, It was more like surface level analysis, pulling out specific pieces of info, maybe spotting relationships between words, but not really getting at the deeper meaning. Like they could maybe tell you who did what to whom and when, but not really why, not the nuances, not the deeper implications.
So like the system might notice that Cat and Matt often appear together, but it wouldn't really understand the relationship between them, like it wouldn't get the concept of a cat sitting on a mat.
Exactly. And that leads us to where the field is now. There's a growing feeling that like to get to that deeper level of understanding, you need to combine those formal logic-based approaches from the early days with the power of, corpus-based statistics. And there's also really cool work being done on integrating connectionist methods like, neural networks with those, symbolic and logical frameworks. It's almost like the field is like trying to get the best of both worlds.
Yeah, like realizing that understanding language isn't just about like recognizing patterns, but also about reasoning and like making inferences, which often need like a more structured logical approach.
Yeah.
And if you want to dig deeper into the field in general, the SETP entry recommends some great books like Allen's Natural Language Understanding, Jurafsky and Martin's Speech and Language Processing, and the one by Clark and colleagues. So going back to that shift towards statistical NLP, we were talking about how advancements in speech recognition played a part in that, right? Mm. And a key concept that came out of that period is the hidden Markov model, or HMM. What's interesting about these HMMs is that they try to like model the uncertainty, the noisiness of language,
Yeah.
Like think about how often we mishear things or we mumble or, we say things a little bit differently. It's like language isn't always perfectly clear.
Yeah, it's true. And HMMs are really clever because they imagine there's like this underlying true message hidden beneath all that noise, and they use probabilities to try and like figure out what that true message most likely is.
Exactly. And that's perfect for spoken language because, you have hesitations, you have people mispronouncing things, different accents. It's all pretty messy. And HMMs model this by like saying there's this hidden layer of underlying states. So that might be the actual sequence of words being spoken. And those hidden states, they generate the observable sequence, which is, what we actually hear. And that might be noisy, distorted in some way.
And those hidden states, they can represent like those more abstract, higher level linguistic units, right? So like you might have a sequence of raw acoustic signals, and those might be like probabilistically generated by a sequence of phonemes, the basic units of sound in a language. And then those phonemes, they might generate a sequence of words and then maybe even parts of speech. It's like a chain.
Yeah, and what's really cool is that the model actually learns the probabilities of those hidden states and the transitions between them, like how likely it is to go from one state to another. And it learns these probabilities from like training data. So it essentially learns, how likely certain word sequences are and how they usually correspond to those acoustic signals.
And then once it's trained, you can apply that HMM to, some new data that it's never seen before. And you use these like really efficient algorithms, like the Viterbi algorithm, to figure out the most probable sequence of those hidden states. So essentially you're figuring out like what someone probably said, even if their speech was, a little mumbled or there was some noise in the background.
It's like the algorithm is trying to clean up the audio and figure out what's really being said.
Yeah, exactly. And those techniques, they were originally developed for like speech recognition, but they turned out to be so useful that they were quickly generalized to like higher level linguistic structures. And now they're used in pretty much every area of NLP.
Yeah, it really shows like how powerful probabilistic modeling can be when you're dealing with all that uncertainty in language.
Yeah.
Now, another major area of research, and one that takes a very different approach, is connectionist models, or as they're often called, neural networks. And what's really interesting about these models from like a philosophical perspective is how they handle sequences of info over time, how they combine different parts of a sentence. And they do all this without like relying on explicitly stated rules. Instead, they learn these complex patterns from like huge amounts of data.
Yeah, it is a totally different paradigm, right? So you don't have this like system built on rules and logical structures. Instead, you have these like massive networks of interconnected units that learn from the data. But, one of the big questions is like, how do they handle the fact that language is sequential? Like the order of words matters.
Yeah, that's a good point. So how do they do that?
Well, there are like two main approaches. You have simple recurrent networks, or SRNs, and these use feedback connections to these special units called context units. And these units, they essentially store a representation of like what the network did before. So it's kind of like a short-term memory. So when the network processes a new word in a sentence, it can look at that word, but it can also see what came before it.
Right. So it's like it can keep track of the beginning of a sentence and use that info to understand the end. And you also mentioned localist networks. How do those work?
So in localist networks, the basic idea is that each unit in the network, it represents a specific concept or a linguistic entity. And when a concept becomes relevant in the input, like you hear a word that represents that concept, the corresponding unit in the network, it becomes active and it stays active for a bit. And this means that like you can have multiple concepts active at the same time representing different parts of the sentence.
Okay, but if you have multiple concepts active at the same time, how does the system know like which properties or features go with which concept? Doesn't that lead to like a jumbled mess?
That's exactly the problem. It's called the variable binding problem. So imagine you have like two boxes, one red and one blue, and you have labels color and shape. How does the network know which label goes with which box, especially if both boxes are like active at the same time? That's the essence of variable binding, making sure that the right attributes are linked to the right entities. And there are various solutions that have been proposed, one of which is using like synchronized patterns of neural activity, like synchronized pulse strains. So units that represent the same entity, they might fire together in a coordinated way.
Interesting. It's almost like a neural version of tagging or indexing.
Yeah.
And it sounds like connectionist research isn't happening in a vacuum, like it's not totally separated from more traditional linguistic ideas.
Right. There's this trend towards integrating ideas from symbolic processing. So a lot of researchers now think that even in these connectionist frameworks, the ultimate goal of parsing is to like get to a representation of the underlying phrase structure of a sentence. And the network learns to pick the best structure by like adhering to certain implicit constraints or biases, which are kind of like symbolic rules in a way.
So it's going beyond just recognizing patterns and actually incorporating like a sensitivity to the structure of language.
Exactly. And we're seeing all sorts of cool hybridization happening now. Like you have neural networks interacting with symbolic data structures like stacks, or using neural nets to learn the probabilities for those statistical parsers we talked about earlier. And there are even systems where the parser network communicates with a separate network that does prediction and learning. It's a very dynamic area. And if you want to learn more about that, Mark Crocker's work on connectionist sentence processing and these hybrid methods is a great place to start.
So the Stanford Encyclopedia entry also talks about these things called syntactic preferences, and these are like these interesting tendencies in how we humans tend to interpret the structure of sentences, even when there might be like more than one grammatically valid way to do it.
And what's so fascinating about these preferences is that they kind of hint at these like underlying biases and how our minds process language. Like, for example, there's this thing called the right attachment preference, which is basically our tendency to like attach new words or phrases to the most recent part of the sentence we've heard.
Right, like in the example they give, he bought the book that I had selected for Mary. We naturally assume that for Mary is telling us who I selected the book for, not, that Mary's the one he bought the book for.
Mm-hmm. Exactly. But then there are these like counterexamples to that, like she carried the groceries for Mary. Here, we assume that for Mary is telling us who benefited from the carrying, not that the groceries were like a special kind intended for Mary, even though like the right attachment preference would suggest that second interpretation. So it seems like there are these other factors at play as well, like maybe a preference for the modifier to be closer to the verb semantically.
Yeah, it's like our brains are trying to make sense of things, not just blindly following rules. Mm-hmm. And there's also the late preposition effect. So like in the sentence, she describes men who have worked on farms as cowboys. We're more likely to interpret as cowboys as referring to her act of describe, not, like describing the men's profession while they were working on farms.
And these are just a few examples, but they really highlight how even basic syntactic processing is actually incredibly complex. And then there's this other interesting phenomenon, the preference for parallel structure in coordination.
Right, so like in the sentence, they ask for tea and coffee with sugar. We tend to group tea and coffee together and then apply with sugar to both. Even though grammatically, coffee with sugar could be like a separate item.
Precisely. And all these examples, they show us that our minds aren't just, blank slates. We have these built-in biases and expectations when we're processing language. And these are the kinds of subtle mechanisms that computational models need to be able to account for.
And that kind of brings us into the realm of meaning, right? And the entry goes into a lot of detail about logicist approaches to meaning representation. And this is where it gets really philosophical.
Definitely. The logicist perspective, it takes a very direct stance on the relationship between language and thought, saying that essentially language itself, especially when you make its structure explicit through parsing, it is a form of logical meaning representation. So to understand a sentence means to map it onto a logical structure.
So it's like when we understand a sentence, we're basically translating it into a logical notation in our heads,
Yeah.
Like with variables and operators and stuff.
That's the basic idea. And this veer, it doesn't necessarily, say anything specific about what those mental representations actually look like in our brains. But it does suggest that, based on principles like Occam's razor and the idea of coevolution, that our mentalese, the hypothetical language of thought, it might itself be, fundamentally language-like and logical.
Now, one common objection to this view is that, human thinking isn't logical in that formal sense. So how do logicists respond to that?
Well, they typically argue that saying there's a logical foundation for meaning representation doesn't mean we can't also use other forms of reasoning, right? So you have deductive reasoning, but you also have inductive reasoning, abductive reasoning, all these less formal, non-deductive processes. And they see logic as kind of like the scaffolding for these other cognitive processes to operate on.
Okay, that makes sense. And what about the fact that we often forget the exact words of like something we hear or read, but we still remember the meaning?
Logicists explain that through the idea of canonicalization, which is like taking the linguistic input and reducing it to a standard logical form. And they also say that our memory focuses on the core semantic content, the logical entailments, and we tend to forget those, more superficial aspects of the wording.
So we remember the underlying logic, not the exact words.
Right.
And does this logicist perspective exclude the possibility of other kinds of thought, like, visual imagery or other non-linguistic representations?
No, not at all. A lot of logicists acknowledge that there's probably some interaction between that language-like, logical mentalese, and other modes of thought. And they point to research like Paivio's dual coding theory, which says there are both verbal and visual systems for representing information.
So it's not just logic, but logic plays a central role.
Yeah, that's the idea.
Now, as structured as this approach is, the entry brings up some important concerns about how expressive these semantic representations are. Language is so rich, it can express so many complex ideas. Can these formal logical systems really capture all that?
That's a crucial question. And the expressivity of the semantic representation language, it's all about, how well it can represent different linguistic phenomena, like, references to events in time, those weird quantifiers like most or few, the whole mess that is plurals, different kinds of modification, modalities like possibility and necessity, and even reification, treating abstract concepts as if they were concrete things. All of these things need to be captured accurately for a system to really understand and generate language.
Let's take, for example, like referring to events and situations. We do that all the time in language. We talk about events. We use pronouns to refer back to them. We describe their properties.
Yeah, like Molly barked loudly last night for several minutes. This woke up the neighbors. So in that second sentence, we're using this to refer to that specific barking event. And the Davidsonian framework, it deals with this by introducing event variables into the logical representation. So you'd explicitly represent that marching as an event, link it to Molly, the time, the manner of barking, all that.
So there exists an event E such that the agent of E is Molly, the action of E is barking, the manner of E is loudly, and the time of E was last night for several minutes. And then this in the next sentence refers back to that E.
Exactly. But the examples get even trickier, like sentences with negation or quantification. No rain fell for a month, and this caused widespread crop failures. So even though there was no rain, that lack of rain is still treated as an event that can be referred back to. And there are other frameworks for dealing with this, like Barwise and Perry's situation semantics, or Hubert's extensions of first-order logic. They all try to capture this link between language and the events or situations it describes.
And then you have plurals, which seems simple on the surface, but are actually pretty complicated, like people gathered in the town square.
Yeah, so you have people, which refers to a bunch of individuals, not just one, and then gathered, which applies to that whole collection. And most formal approaches to plurals, they introduce a plural operator that can, map those singular predicates to their plural versions. And these approaches often use this mathematical structure called a joined semilattice to model the relationships between those collections.
It's like taking the singular predicate person and turning it into a plural predicate that can apply to a group of people as a unit.
Yeah. And then there's this whole issue of ambiguity between collective and distributive readings of plurals, like the children ate a pizza. Did they share one pizza, or did each kid have their own? So a lot of formal theories say that plural noun phrases are just ambiguous. They can refer to either a collection as a whole or to each member individually. And the main point here is that to really represent plurals, you need to go beyond basic first-order logic. You need a more expressive system.
And the last big topic on expressivity is intentionality, which deals with beliefs, desires, propositional attitudes, and things like necessity and possibility. So John believes that the universe is infinite. How do you represent that belief formally?
One common way is to use this special operator called holds, which takes an agent, a proposition, and a time as arguments. So you could say holds believes. But things get really tricky when you have quantification within these intentional contexts. Like John believes that every galaxy harbors some life form. This has both a wide scope and a narrow scope reading for every galaxy. And standard first-order logic struggles with that narrow scope reading.
Right. So it's does the belief apply to each specific galaxy or to the general idea that all galaxies have life?
Exactly. And there are other approaches, like using eventuality arguments, where every predication is linked to an eventuality, and then you say whether that eventuality occurs. And a lot of the motivation for these approaches is to be able to use the, well-established tools of first-order logic. But as the entry points out, there's not really strong evidence that inferences that are easy in first-order logic are actually easier for humans, you know? This has led to research in areas like natural logic, which tries to build systems that reason directly with natural language, kind of like Montague grammar.
So it seems like the search for the best way to represent meaning is still ongoing.
Definitely. And the choice of which semantic tool to use often depends on what you're trying to achieve with your computational system. So if you're building a dialogue-based problem-solving system, for example, you probably need logical or symbolic representations that support really strong reasoning and inference, because with those systems, you need them to track intentions, keep track of constraints, and come up with solutions logically.
They need to actually understand the problem and reason through it, not just match keywords.
Exactly. But for other tasks, like image recognition or judging how similar words are or figuring out the sentiment of a text, you might need those symbolic representations. And in those cases, statistical methods can work really well. But the general trend seems to be towards, combining these different approaches.
So it's not about finding one perfect tool, but rather the right tool for the job.
Right. And within statistical NLP, there's this increasing focus on moving beyond just like pattern recognition and towards interpretations that you can use for more complex tasks, like inference and question answering. And some researchers are even exploring using like natural language text itself as the basis for inference. And then there's this work on building statistical semantic parsers, which try to automatically produce logical forms from natural language data.
That sounds like a really crucial bridge between the power of statistical learning and the rigor of, symbolic representation.
It is. But as the entry points out, even simple things like figuring out the scope of quantifiers, like in the sentence, every child at the picnic was roasting a wiener, can depend on subtle aspects of our world knowledge that go beyond just like word co-occurrence statistics. And then you have habitual and generic sentences like racehorses are often skittish. These are really hard because they have these temporal ambiguities and implicit quantifiers, and you need a lot of background knowledge to understand them.
Like you need to know about horse racing, the temperament of horses, what often implies in this context, it's not just about the words themselves.
Exactly. And that brings us to another key aspect of language understanding, which is core friends resolution. So this is the task of figuring out which noun phrases in a text refer to the same entity. And it's surprisingly hard for computers, even though we humans do it all the time without even thinking about it.
Yeah, like we just know that he refers to John, even if John was mentioned like 5 sentences ago. But how do you teach a computer to do that?
Well, there are these linguistic principles that guide us, like agreement and gender and number, syntactic constraints like C command, and things like recency and salience, which entities are most important in the discourse. Early rule-based algorithms, like Hobbes's algorithm, they tried to capture some of these regularities, but semantic information also plays a role, like selectional preferences. Knowing that, spill usually takes a liquid as its object. And then there's that classic example from Winograd, the city council example, where the interpretation of a pronoun depends entirely on our world knowledge and the specific verb used.
Right, so like the city council refused the women in parade permit because they feared violence versus because they advocated violence. Who they refers to changes completely depending on whether we think the council or the women are more likely to fear or advocate violence.
Exactly. And core friends gets even more complicated when you have references to groups or related entities or abstract things like propositions and events, things that aren't even explicitly mentioned as noun phrases. So nowadays, statistical techniques are often used to try and resolve these ambiguities, taking into account all sorts of features like the linguistic and pragmatic factors we talked about, as well as things like animacy, how often entities have been co-referenced before, and parameters learned from those big annotated text corpora.
The entry also briefly mentions discourse relations, which is how clauses and segments of text are connected to create a coherent whole.
Yeah, so you have relations like elaboration, giving more detail about something, exemplification, providing an example, parallelism, using similar structures, and contrast, highlighting differences. These are really important for understanding how a text flows and what it means overall, but the entry saves that discussion for the section on language generation.
Which brings us to figurative language, something that's always been a challenge for computational systems. We talked about metonymy, but metaphor seems particularly tricky.
It is, and some people argue that metaphor isn't just a stylistic thing. It's actually woven into how we use language all the time, blurring the lines between literal and figurative. Like, take the expression, the temperature dropped. We understand this literally, degrees on a thermometer, but it also evokes this image of something physically going down.
And understanding metaphors goes beyond just, like, loosening up our semantic expectations. It depends a lot on the context and our background knowledge, like the phrase, he threw in the towel.
Exactly. You need to know about boxing, that throwing a towel into the ring means giving up. And because metaphor is so dependent on context and knowledge, building a system that can understand and generate metaphors creatively is still a huge challenge. Early attempts, like Martin's Midas program, they relied on hand-coded knowledge about specific domains and metaphors. But more recent research uses statistical approaches, leveraging things like WordNet and big data sets to find similarities between concepts that might underlie metaphorical connections.
It's like trying to teach a computer to see those conceptual links between the source and target domains, not just understand the individual words.
Right. And then you have the whole problem of ambiguity and underspecification in language. Words and sentences can have multiple meanings or they might leave things unsaid, and this makes reasoning and inference really hard. So the entry talks about these different frameworks for resolving these issues, like weighted abduction, constraint solving, and loose speak interpretation.
Weighted abduction is like, you know, finding the most plausible interpretation based on what we already know, maybe adding in some assumptions. Constraint solving sees interpretation as like trying to satisfy a bunch of constraints from syntax, semantics, pragmatics, context, world knowledge, all at the same time. And loose speak is about how we often interpret things more flexibly than a strictly literal reading would allow, especially with things like nominal compounds and metonymy.
And these frameworks, they try to find the best interpretation by looking at all these interacting factors. But sometimes, even when our world knowledge points in one direction, we might go with a simpler interpretation. And Winograd's city council example reminds us that sometimes those learned patterns and associations are more important than formal logic when it comes to disambiguation.
It's like our brains are constantly weighing different possibilities and integrating different kinds of information to make sense of what we hear.
Absolutely. And that suggests that, those statistical methods that have been so successful in other areas of NLP might also be useful for modeling these complex disambiguation processes.
Now, shifting gears a bit, the entry also talks about language generation, which is like the flip side of understanding. It's about taking our thoughts and ideas and putting them into words.
And you could say that it's the inverse of understanding, right? You start with some internal representation, your intended message, and then you have to make all these decisions. What to include, how to organize it, what words to use, what grammatical structures, how to structure the discourse.
And content planning seems like a key part of that, figuring out like how much detail to include, how broad or narrow the scope should be.
Absolutely. And it depends on what you're trying to do, right? Whether it's a detailed description, a narrative, a persuasive argument, or just a simple statement of fact. For those more complex tasks, organization is crucial. Narratives often follow a chronological order. Arguments build up to a conclusion, descriptions go from general to specific, and those rhetorical relations become really important, signaling the relationships between different parts of the text.
Like using, on the other hand, to signal a contrast.
Exactly, and all of this depends on having access to different kinds of knowledge, from dictionaries and resources like WordNet and FrameNet, to more formalized world knowledge found in databases, gazetteers, and even Wikipedia. But as the entry points out, a lot of our everyday common sense knowledge isn't so easily captured in those structured formats.
Which brings us to crowdsourcing, using the collective intelligence of like internet users to gather information.